Wonderful. Upper triangle matrix. Now we are going to discuss about lower triangle matrix. Lower triangular matrix. A square matrix. It is also square matrix. Is said to be lower triangle matrix. Triangular or triangle matrix. If one only. What I mean by upper triangle, the diagonals, all the entries below the diagonals are 0. So here, all the entries above the diagonal, principal diagonal are 0. That means if you take A is a matrix, A is a, this is n by n matrix, right? So A is a lower triangle. If one only, A is A0, if I is less than J. That means your matrix should be in a form of this one. So for example, you can take this 1, suppose you can take 0, 0, 2, 3, 0, 4, 5, 6. So that means it is nothing but a lower triangle matrix, because actually what, this is my diagonal, this is a square matrix, it's a diagonal. So above the diagonal are all 0. So this is 0, this is 0, this is 0. So therefore this is lower triangle. Lower triangular matrix. Right? Suppose you can take this A equals to, this 1, minus 1, 0, 2, 3, 0, 4, 5, 6. Is it lower triangle? No, right? Is it lower triangular?
No, sir.
Right? At least one entry above the diagonal. This is a non-zero, therefore not lower triangle. Not lower triangle. Right. Next is, suppose you can take A is a matrix. Suppose you can take S is a matrix. What is that? Set of all n cross n lower triangular matrices. Lower triangular matrices of order n by n. So first question is minimum number of zeros. Number of zeros in S. So minimum number of the lower in a lower triangular matrix of order. Oops, don't take this. Don't take this. Minimum number of zeros in a lower triangular matrix. Don't take this. What is it? Minimum number of zeros, lower triangular matrix. Matrix of order n by n. Now tell me minimum number of zeros. How many zeros?
N into n minus 1 by 2.
That's it. So that means this is my A11, 0, 0, 0, 0. This is A21, A22, 0, 0, 0, 0, A31, A32, A33, so 0. That means AN1, AN2, going on, ANN. That means how many zeros are there here? In this row, how many zeros? N minus 1.
N minus 1.
In this row, n minus 2 zeros. So in last one, we're going to get 1. Therefore, total is n minus 1 into n minus 1 by 2. So this is required. Right? Similarly, Maximum number of zeros. Maximum number of zeros.
N square.
Number of zeros in the lower triangle matrix is n square. Same idea is n square. And question is maximum number of non-zeros. Maximum number of non-zeros in a lower triangle. Maximum number of non-zeros. Tell me. So this, actually this could not be actually 0. So therefore, how many entries? N. Similarly, this is n minus 1. Going on. This is 1. So total entries, non-zero entries could be n plus n minus 1. Going on. 1. 2 plus 1. That is n into n plus 1 by 2. Is it clear? Hello? Number of non-zeros. So the a1 1 cannot be 0. Understand? Cannot be 0. So therefore 1. This is 2 and this how many entries here? 2 entries. This is 3 entries. So going on n entries. Total sum is n into n plus 1 by 2. Right? Next is maximum number of distinct elements. Tell me. Maximum number of distinct elements in a lower triangle matrix. Anybody?
+1, sir. Pi then +1.
Good. So distinct means here 0 can be added. Yes or no? 0 can be added. So this is answer, right? So this could be distinct. I need actually this could be distinct, and 0 also distinct. One of the distinct. Therefore, you can add 1. So therefore, what is the required answer? N into n plus 1 by 2 plus 1. Right? Now tell me minimum number of distinct elements.
1.
Only 1. Minimum number of distinct elements in a lower triangular matrix is only 1, because this could be 0. See, all the entries could be 0 because in the above diagonal all are 0. So therefore, minimum number of zeros, minimum number of distinct elements I need. Therefore, this all could be 0. Therefore, the answer is only one possibility. The answer is only 1. Right? Next 8 is you can take any addition. Means what? Sum of the two any lower triangle matrix. Sum of 2. So did I mention actually sum? No, right? Okay. Next, I want to define comparable. When do you say that comparable? What do you mean by comparable? When do you say that two matrices are comparable? So we say that A and B.
Order is same.
Yeah, order is same. So A and B are M cross N matrix, or A and B are two matrices. So A and B are comparable if and only if size of the matrix or order of the matrices, order of A and B are same, are equal. Right? Suppose you can take this A equals to 1, 2, 3, 4, B equals to 1, 2. Are they comparable? No, right? This is 2 by 2. This is 1 by 2. Therefore, order is different. Therefore, they are not comparable. They are not.
Sir, good evening.
Good evening.
Sir,
Right. Next is if you take this A equals to 1, 2, 3, 4. Suppose B equals to suppose A, B, C, D. Are they comparable? Yes, because order is same. This is 2 by 2 matrix. This is also 2 by 2 matrix. Therefore, they are comparable. Right. Next is equal matrices. Next is what? Equal matrices. So two matrices A and B are equal if and only if first property is, their sizes are same. That means they are comparable. Right. Second is, corresponding entries. Corresponding entries or elements of A and B are same. That means suppose you can take A equals to Aj. So order should be same. Therefore, A equals to Aj, B equals to Baj, 1 cross n. So addition, this equality matrix are permittable, are acceptable, equal for equal matrix. This order must be same. So A and B are equal matrix. Of course, you can take different matrices also. Suppose you can take P cross Q. So A and B are equal matrix if and only if. So what is my first property? This order must be same. That means what? M equals to P and N equals to Q. Second property, so Aj equals to Baj for all Ij. Right? For all Ij. So let us start with the simplest example. Suppose you can take A equals to 1, 2, 3, 4. B equals to, suppose A 3, 5, 6. Right? So if A and B are same, what is A value? You know that A equals to 1. Right? That means these sizes are same. Sizes are same. So corresponding entries should be same. So A equals to 1. Suppose you can take the example. Suppose A equals to 1, 8. A, B equals to 3, 4, 7, 8. Question is, under what conditions A equals to B? First one. If so, this is my first question. Second question, if so, if they are equal, what are A and B? What are A and B? Under what conditions? My question is, under what conditions they are equal? If so, what are A and B? Right. Anybody?
One equal to 3 and 8 equal to 4.
Yeah, that means A equals to B if and only if, already sizes are same. Sizes are same. So what is my definition? What is my definition? Corresponding entries should be same. That means 1 equals to 3 and 8 equals to 4. Right? A equals to 7, B equals to 8. So 1 equals to 3 is possible if and only 3 minus 1 equals to 0. Right? 3 minus 1 equals to 0.
0.
So that means 2 equals to 0. So when do you say that 2 equals to 0? It is possible whenever it is Z2.
Yes.
Right? So in Z2, 2 equals to 0 and 8 equals to 4, because actually 8 equals to 4 means what? It is congruent to 0 modulo 2. Yes or no? So 8 equals to 0 and 4 also equals to 0. Therefore, it is possible in only field Z2. Yes or no? Yes. So therefore, so in the field Z2, A equals to B. What is my condition? In the field Z2, A equals to B. That is my first answer. Second answer, if so, in Z field 2, if you take a field Z2, what is my A? My A is actually 7, but this is congruent to 1 modulo 2. So that means my A is what? Actually 1. What is my B? My B is actually 8, but actually we are
0.
working in a field, Z2, therefore this is congruent to 0
0.
modulo 2. So what is answer A? 1, B equals to 0. Is it clear? Right?
Yes.
So next is, suppose you can take this. Suppose A equals to 5, 0, 1, 1, B equals to 2, 3, 4, 7. So A equals to B if A equals my field F is equals to real field. My field F is equals to suppose complex field. My field F is equals to Z5. My field F is equals to Z3. So when we say that A equals to B, see clearly the dimensions are same, the orders are same. So in order to say that A and B are equal, so we need to say that actually the orders are same and the corresponding entries are same. But here clearly, unfortunately, the orders are same. It's enough to check whether the corresponding entries are same or not. You need to check it, right? Corresponding entries should be same. That means y equals to 2. So 5 equals to 2, 0 equals to 3, and 1 equals to 4, and 1
Equal
equals
to
to
Z3.
7. That means, yeah, 5 minus 2 equals good. 5 minus 2 equals to 0. That means 3 equals to 0. 3 equals to 0 is possible if my field is Z3. So in field Z3, that 3 equals to 0. Of course, this is redundantly true because 4 equals to 1 in Z3. 4 equals to 1 in Z3, that is true. And 7 also equals to 1 in Z3. So this condition hold, this condition hold, this condition hold in Z3. So what is my answer? Z3. So in a field Z3, A equals to B. In a field Z3, A equals to B. Right. Next is, did I mention that addition property? Addition yesterday class, addition of matrices. No, right? Yeah. Next is addition. Yeah. Once you have a comparable, then we need to define addition of matrices. So addition of matrices means you take A and B are of matrices of same sizes to matrices of same order. So for sake of our convenience, I'm going to take M cross N over a field F. So their addition is defined by like this. So ijth entry of A plus, see, this addition is denoted by addition of A and B denoted by A plus B and is defined by like this. So addition of ijth entry of A plus B is same as saying that ijth entry of A plus ijth entry of B. This is true for every I equals to 1 to n. This is true for every j equals to 1 to n. Right? So ijth entry of A plus, that means what is this? Actually, this addition of A plus B is defined by adding the, what you're getting A plus B. A plus B is a matrix of the same order, right? In which, how can you get the elements? The elements are obtained by the adding the corresponding elements of A and B. That's what actually definition, right? So A plus ijth entry of A plus by B is nothing but ijth entry of A plus ijth entry of B. That means A plus B is a matrix of order of same order in which every element is obtained by adding the corresponding entries, adding the corresponding elements or entries, elements of A and B. So this is what actually definition. So A plus B also is a matrix of the same order, right? Suppose you can take this. For loss of generality, I can take 2 by 2 for convenience. Right? What is A plus B? Simply one can take it as 5. That means 1 plus 4, 5, 2 plus 5, 7 plus 6, 9, 4 plus 7, 11. Right? So this is what actually A plus B. Right? A plus B is permissible, actually acceptable. You know, order of the matrices are same. Order of the matrices are same. Right? Suppose you can take A equals to 1, 2, 3, 4, B equals to like 3, 5. So can it be possible for addition? No, because the orders are different. Because the orders are different. This is 2 by 1. Orders are different means what? Not possible for addition. Addition. Right? You know it. Right? So addition is possible. Addition of matrices is possible only for the matrices which are of the same order. Which are of the same order. Right? Next is properties. properties of addition of matrices. Addition of so these are useful to define a vector space. First one is that addition of matrices, of course, matrix addition or addition of matrices, you can call it as any name. Matrix addition is commutative or abelian in other language. Commutative. That means you take any two matrices of same order. If you add a plus b, that gives the same value b plus a. So a plus b is same as saying that b plus a. You take any two matrices of same order. That means matrix addition is commutative, right? Second is matrix addition is associative. Means addition of matrices right is associative. That means you take a, you take b, you take c. If you add b plus c, then add to a. The same as saying that a plus b plus c. This is true for any three elements which are in a matrices, right? So addition of matrices is always associative. Next is additive identity. It satisfies additive identity property. That means you give me any matrix of order m by n. There exists a matrix, which we call it as zero matrix, right? Such that a plus 0 is same as saying that 0 plus, you know, these arguments in group theory. This is true. So here 0 is nothing but what? Additive identity. Additive identity. What is 0? 0 is nothing but 0, 0, 0, 0, going on like this. M by n matrix. Right? So it satisfies identity law with respect to addition. Similarly, additive inverse. In short, inverse law with respect to addition. That means you give me any matrix, M by n matrix, I can find an inverse, which we call it, which is denoted by minus a. Such that a plus minus a equals to minus a plus a equals to 0 matrix. So this we call it as actually inverse, additive inverse. You can easily check it, you know, these are equal matrices. You need to check it easily by taking the corresponding entries, by showing that the corresponding entries of a plus I 0 is same as saying that 0 plus a corresponding entries. It's enough to show that corresponding entries of a plus 0 is same as saying that 0 plus a. That means it's enough to show that corresponding entries of this is same as saying that corresponding entries of this is same as saying that corresponding entries of this. This is true for every ij. You need to check it. You need to check it. It's an exercise. It's simple exercise. You have to check it. It's straightforward. So this is the additive inverse of a matrix A. See, it is not a social sciences, right? You need to fill the gaps. Whenever something is given as an exercise, you need to fill the gap. It is not memory based subject. This is a property you mug up. This is a property you mug up. This is not like the subject as a social sciences, right? But I'm not criticizing the social subject. But the thing is, this is not a subject. This is not a subject as like, you know, in like a sociology, biology, like zoology. You need to fill the gap. How we can get this a plus 0 is equals to 0 plus a is equals to a, right? Right? This is additive inverse. Here, minus a is nothing but additive. Suppose you take a equals to 1 to 3. What is additive inverse? Anybody? What is additive
Minus
inverse?
one, minus 1, minus 2, minus 3, minus 4.
minus 3, minus 4.
Yeah, this is minus 3, minus 4, right? So this is additive inverse, right? So again, you know that, see, the matrix satisfies, you know, this commutative, you know, associative, you know, identity law and inverse law. That means what? In the If the matrix set of all matrices
Is
M by n
called
matrices satisfying this all
group.
in fact
Group.
abelian group, right? In fact
Abelian group. Yes.
abelian group. That means set of all matrices with respect to addition is an abelian group. With respect to matrix addition. That is set of all matrices M by n matrices is an abelian group. With respect to addition of matrices. Yeah. Now, next one, once it is a group, automatically every group satisfies cancellation loss, right? So cancellation loss hold in the set of all matrices in a, set of all M by n matrices. In fact, you need to take this notation. Set of all matrices with respect to addition. That means A plus C. Suppose you can take this C plus A is equals to C plus B. If this happens, automatically A equals to B. What is this? Left cancellation law. Right? Why? Because it's an abelian group. Any group satisfies cancellation loss with respect to that operation. Right? So this is B plus C. Then that equals to A equals to B. This is right cancellation law. Right? Next is, suppose you are given a equation. You are given a matrices A and B are matrices of order M by n. Question is, if you take this equation, how many solutions it has? How many solutions? Anybody? Unique solution, because you're in group. Every group, when you take any group, any linear equation has a unique solution because it's a group. So group satisfies inverse property. There is inverse for every element you take. So definitely it has a unique solution. So what is the solution? Anybody?
A inverse into B.
Yeah, what is that? See, you are working with respect to addition. You are working with respect to matrices with respect
B
to
minus
addition.
A.
Yeah, right.
Minus
That is
A
equals to X is equals to, yeah, minus A. So this is my solution. It is a unique solution, right? Next is actually difference of matrices. Matrix addition. What is matrix addition? Set of all matrices with respect to addition is an abelian group. Suppose you can take the difference of matrices. Right? Suppose you can take this. Right? What is the difference of matrices? Suppose you can take A and B same sizes. A and B and matrices of same order. Loss of generality, I can take M by N. So difference of two matrices is denoted by A minus B, right? And ijth entry of this A minus B is defined by, this can be obtained by ijth entry of A minus ijth entry of B. This is true for every ij, right? So order must be same. That order must be same. In order to difference, that means in order to subtract the elements, subtract the two matrices, order must be same, right? So these are of the same sizes. These two are matrices of the same sizes. Therefore, A minus B is what? 1 minus 1. See, orders are same. So it's enough to subtract the corresponding elements. So 1 minus 1, 0. 2 minus 2, 0. 3 minus 0, 3. 4 minus 0, 4. Right? Suppose you can take this. A equals to 1, 2, 3, 4. B equals to 1, 2. Is it possible for difference? No. not permissible, right? Because order is 2 by 2. This is 1 by 2. So difference of matrices is not possible, right? Is it a group actually? Anybody? Is it a group with respect to difference?
No,
No,
sir.
sir.
Right? Set of all m by n matrices with respect to difference. With respect to difference of matrices, is it a group? No. But what property is going to fail? Anybody?
Commutative, sir.
Associated.
Group. I'm not asking abelian group. Yeah, associative could be fail. Associative could be fail. Right. So you need to give a 3 matrices. It's an exercise. Give 3 matrices ABC, which fails to satisfy A minus B plus C equals to A minus B minus C. You need to show it. Give me 3 matrices. It's an exercise, simple exercise. You need to take any 3 matrices. You need to give 3 matrices. You need to check that A minus B, A minus B minus C equals to A minus B minus C. Are they equal or not? You need to check it. So of course it fails to satisfy. Of course it does not satisfy associative property. You need to check it. Right? It's not a group. It's not a group. Right? Next is, so if it is not a group, it is not useful. Right? Next is scalar multiplication. So what is scalar multiplication? Suppose you take any matrix of order m by n. You take any matrix of order m by n. Right? K is any scalar. You can take any scalar for a field K f. So scalar multiplication of a matrix with a scalar is denoted by Ka. Right? Scalar multiplication of a matrix A with a scalar K is denoted by Ka, which is obtained by, that means his ijth entry is obtained by K into corresponding ijth entry of A. This is a definition. Right? ijth entry of K is nothing but K times of ijth entry of A. Right? It is also straightforward. Suppose you can take K equals to 1, 2, 3, 4. Suppose I can take K equals to 2. It's a real number. Therefore, what is 2 into A? Means you multiply each entry by 2. 2 into 1, 2. 2 into 2, 4. 2 into 3, 6. 2 into 8. 2 into 4, 8. So this is what actually, right? Scalar multiplication. Right? So this is useful for a vector space. So this is very, very useful property. Right? So properties. Whenever you take a matrix, whenever you take any matrix, you take any scalar, you take any 2 scalars, K1 and K2. K1 plus K2 of A is equals to K1A plus K2A. Right? And K1 K2 of A is equals to K1 into K2A. This is true for any 2 scalars. You take any field for any matrix of m by n. Right? Next is K into A plus B is equal to K into A plus K into B. Right? This is true for any scalar and any matrix of m by n. Right? Next, 1 into A equals to A. You can check it. See, you can check it, Amma. You can check it with straightforward proofs. You can check it. Right? Next is 0 into A equals to, see, this is 0 number, real number, scalar. It's not a matrix. So 0 into matrix is equals to 0 matrix. So if you take this m by n, this also m by n matrix. Right? Next is A into 0 matrix. This is 0 matrix. Suppose it is m by n matrix, you're going to get 0 matrix. Suppose it is nothing but, see, it is the matrix product I am not defined, right? So don't take this. I'm not defined matrix product. Don't take this. Next is, you take any scalar, you take any scalar, you take a zero matrix, what you're going to get? Zero matrix. Suppose you can take this as m by n matrix. This m by n matrix, if you take this also, you can get the same m by n matrix, right? And minus k into a is equals to minus k a equals to k into minus a. So these properties are very, 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 very important, because to define a vector spaces, right, these properties are useful. Right. So, actually, we have seen that it's an abelian group. It's actually what? It's an abelian group. If with a set of all m cross n matrices, it's an abelian group with respect to addition of matrices. We have seen with respect to that and with respect to that, together with that, in addition to that, scalar multiplication, scalar multiplication also hold. When you give me any scalar, you take any scalar, you take any m by n matrix, you take any m by n matrix, automatically you're going to get m by n matrix. Understand? You take any scalar a, you take any scalar k, you can take any matrix for m by n. Your matrix multiplication, that means your scalar multiplication is again a m by n matrix. So it satisfies scalar multiplication property. Understand? It satisfies scalar multiplication property, right? It satisfies scalar multiplication property. This scalar multiplication, this is a dot. This is a dot here. This is a dot. This dot is a function. So this dot, this dot satisfies scalar multiplication property, and this dot, this is a dot, the same dot. The same scalar multiplication satisfies these four properties, right? So therefore, we can conclude that set of all m by n matrices with respect to addition and scalar multiplication is a vector space. We'll see later. It's a vector space over a field. Yeah. This is a final conclusion. Right? Set of all m by n matrices, because actually it's an abelian group with respect to addition. It's an abelian group with respect to addition, and it satisfies scalar multiplication property, and scalar multiplication property satisfies these four properties. Together with this, the set of all m by n matrices with respect to addition and multiplication is a vector space over a field. Yeah. Is it clear? Hello.
Yes, sir. Okay, sir.
So I'm
Okay, sir. Okay.
next is product. Product of two matrices or product of matrices. You can take anything. Right. So A is a matrix. Suppose you can take A is a matrix of m by n. B is a matrix of, suppose you can take P by Q. So product of this A and B denoted by AB, right, is defined. Product is defined if and only if number of columns of first matrix, number of columns of A first matrix equals to number of rows of the second matrix. That is here n equals to P. So in this case, see, in order to define a product, number of columns of the first matrix should be equals to number of rows of the second matrix. If that happens, then one can define a product. Right? In this case, what is the entries? What are the entries? So in this case, ijth entry. How can you get the entries? See, you are getting AB, but how can you write the elements? The elements are writing by using this formula, right? So ijth entry of this is nothing but sum of product of, right? Product of the elements of ith row, right, with the corresponding elements of the jth column, right? Sum of the product of the elements of the ith row of A with the corresponding elements of the jth column of the matrix, right? So this is nothing but ijth entry. This is nothing but what? Ijth entry. This is true for every ij. In fact, I is running from 1 to m, right? So this is possible whenever the first number of columns of the first matrix is equals to number of rows of the second matrix. Suppose you can take this A equals to suppose 1, 2, 3, right? A equals to 1, 2, 3. Suppose you can take, right, 2 into 1, or else you can take this, not 2 into 1, 2, 1, sorry, this 2, 2, 1. So this is 2 by 2 matrix, this is 1 by 2 matrix. Therefore, A into B is not defined. Why? Because number of columns is not defined. So that means A into B may not exist. That means A into B may not exist. Right? Second one, A into B may not exist. Of course, A into B. Of course, B into A also may not exist. May not exist. Why? Because for the order. What is the problem here? The problem with only order. May not exist. Can you give example? So you can take any matrix of 2 by 3. See, you can give two different orders. Suppose you can give 5 by 4. So A into B is not possible. Of course, B into A also not possible because the number of columns of the first matrix, they are not same. These are not same. Right?
In
So therefore,
previous problem, it is possible, sir.
yeah, it is possible. But for this problem, it is not possible. For this problem, it's not possible. So may not exist. That's what my point. So A into B and B into A may not exist. Right? And A into B may exist, but not equal. But may not equal. Right? You can take anything. Suppose you can take 1, 2, 3, 4. Right? You can take simple matrix. Suppose 1, 1, 0, 0. Or else you can take 1. So A into B is possible because this is 2 by 2 matrix. This is also 2 by 2 matrix. A into B possible. B into A is possible. This is 1, 2, 3, 4, and 1, 1, 0. That means 1 into 2, 1 into 1, 1. 1 plus 2 is nothing but 3. 1, 0 means 1, 3, 4, 7, 3, 0, 3. This is A into B. Right? So this B into A is nothing but what actually? This is 1, 1, 1, 1, 0, and 1, 2, 3, 4. That means 1, 4. So fails. First entry difference. So rendu same not live.
4, 6, 1, 2.
Right? So one entry is different, therefore they are not equal. So no need to compute this, all these things. Right? This first entry is actually what? First entry, 1, 1 entry of the both matrices AB and BA are not equal. Hence, AB not equals to BA. So that means AB and BA may exist, but they are not equal. They may not equal. They may not equal. Is it clear? So that means what is the property? Matrix multiplication of matrices or matrix multiplication may not be commutative. Matrix multiplication may not be commutative. Right? Matrix multiplication may not be commutative. Right? This is an example. Right? So already told you some special cases, you take suppose diagonal matrices, suppose D1, D2. This is my special case. D1 and D2 are special diagonal matrices. In this case, matrix multiplication is commutative. Understand? Where D1, D2 are diagonal matrices. Of course, A into D is same as, see, you can take any A into D and D into A. This is also commutative. A into D also, D into A also commutative. But the thing is, where D is a scalar matrix. You can check it by taking simplest example. These are some special cases, right? Matrix multiplication in general may not be commutative, but the thing is that if you take diagonal matrices D1 into D2 is equals to D2 into D1 for the matrices of diagonal matrices, and unfortunately A into D into equals to D into A, of course, where D is a scalar matrix may not be, see, this is not actually diagonal matrix. See, you need to take all the entries should be same, otherwise it may not be commutative. Understand? D should be scalar matrix. D should be scalar matrix. Don't take diagonal matrix. Means diagonal entries don't take different. Otherwise, it should not be commutative. Understand? So this is a special case. You can check, right? Next is matrix multiplication or multiplication of matrices is associative. That is A into B plus A into B is equals to A into B into C, right? See, provided they are conformable. So what do you mean by conformable? You know what is meant by, so we say that A and B matrices are conformable if only conformable for the product AB if the number of row columns of A equals to number of rows of B. C, provided A, B, C are conformable. In this case, see, in general, matrix multiplication may not be conformable, but provided here matrix multiplication, provided they are conformable. Right. Next is matrix multiplication is distributive. Matrix multiplication, is a distributive with respect to addition. With respect to addition of matrices. That means A into B plus C is equals to A into B plus A into C. This is left distributive. Next, B plus C into A is equals to BA plus CA. This is right distributive. Right? So matrix multiplication, always distributive with respect to addition of matrices. You can easily check it by taking exercise. You need to prove it, all things. You need to prove it, exercise. All right. Next property. You take any matrix, you multiply with zero matrix, provided they're conformable, you're going to get a zero matrix. You're going to get a zero matrix, provided conformable. That means matrix multiplication is possible. That's what my point. Next is integral powers of a matrix. This is very important concept. Integral powers of a matrix. What do you mean integral powers? You start with any matrix, right? So you take a matrix, don't use notation. So for loss of generality, you can take n by n matrix. Matrix over a field F. So A square is defined by A into A. What is my definition? A square. A square is nothing but what? A into A. What is my A cube? A cube is nothing but A square into A. By induction, A can be written as A minus 1 into A power 1. Right? This is what actually integral powers of A. That means it is also one kind of product. This product of two matrices. This product of this matrix and this matrix. Right? So example, let us start with simplest example. Suppose you can take A equals to -1, 0, 0, 4. Right? Or Question is, what is mean by A3 minus A2? What is mean by A3 minus A2? So what is answer? Anybody? What is answer? Right. What is answer? So don't do product A into A into A. So what is the simple trick I already told yesterday? Since you know it is a diagonal matrix.
1,
It is a
16.
it is a diagonal matrix. Yeah, it is a diagonal matrix. So what you do is that you can take directly whole cube. Understand? So -1 whole square, 0, 0, 4 square. Because it's a diagonal matrix, this is advantage. Already I told you
0, 0, 4,
yesterday.
8.
So that means
0, 0, 4.
-1, 0, 0, 64, -1, 0, 16. So what is it? -2, 0, 0. What is that?
48.
Yes. So that means it is also diagonal matrix because once A is diagonal, product of diagonal is diagonal. You know, this is also product of diagonal, diagonal. Difference of diagonal is always diagonal. So this answer is right. Right. Suppose you can take powers is very important, very important concept. You may see, you may ask for one question. Suppose you can take A equals to 0, 0 minus I. You may be asked for this question. Suppose you are asked to find, suppose, what is A power 100? What is A power 100? So again,
-1,
it is a
0,
feature of diagonal
0,
matrix.
1.
Right? It is again a diagonal matrix. You know. So what is the feature of diagonal matrix? Dia of I power 100 minus I power 100. You know, dia of I power 100. You know what is a, you know, y square is nothing but what? -1. I
-1.
cube equals to minus I. I power 4 is equals to 1. So you need to take the 4 divisor because
I
cyclicity. You know,
power 4, 1.
you know, I is a cyclic group. So therefore, you need to divide with the 100 by 4. Yes or no? So what you do is that I power 25, I power 4 into 25. It can be written as I power 4 into 25. This is minus I power 4 into 25. This is dia of I power 4 is 1, 1 power 25. This is I power minus I power 4 also 1, 1 power 25. That means I power 25 is equals to 25. That means what? 1, 0, 0, 1. Is it clear? This is nothing but exactly your identity matrix. Is it clear? Right? Is it clear?
Yes,
Hello?
sir.
Right? Next is, suppose you're asked to find A200. It's an exercise. A222. It take an exercise. Take an exercise. Right? Using the same technique. Suppose third problem. A and B are two matrices. If A and B are two matrices, right, such that A plus B and A into B are defined, then my question is, square matrices of different order, square matrices, or else see, take rectangular matrices. So rectangular matrices of same order, rectangular matrices of different order. No, square matrices of different order. Next is square matrices of same order. What is the answer?
Square matrices of same order.
Right. Right. So you know, actually already I told you when you want to define. See, they are defined. There are two matrices. They are defined. So for loss of generality, you can take the order should be same, right? The order should be same because A and A plus B is defined means what? They should be same order. They should be have same order. So you are given that A plus B is defined. Of course, A into B also defined. A into B is defined. You know, A into B is defined. Provided what is the order of A? M by N. What is the order of B? M by N. So A into B is defined provided this number of columns of the first matrix is equals to number of rows. That means your rows should be same as saying that your columns. That means A and B are of square matrices of order n by n. That means A and B are of square matrices of same order. So answer is this. Answer is this. Next is you can take for example fourth problem. Suppose you are given 2 3 A plus B equals to 2 3. This is minus 4 this. This is my A minus B. So 1 0 3 5. We're asked to find what is A, what is B. Yeah. What is the idea? Take the addition. Take the addition. So 2 plus 1 is 3. This is 3. Minus 1 plus 2. Minus 1 plus 3 is 2. 4 plus 5, that is 9. So A equals to 1 by 2, 3, 3, 2, 9. So you are getting A. Similarly, one can compute B also. Right? Just take the addition. You can get the A and as well as B. Right. Next is suppose you are given 0, 1, 1, 0. You are asked to find what is A power 5. Integral multiples are very, very important. Go through these questions. Integral multiples A power 100, A power 200, A power 2022. So this type of questions are very, very important. Now what is A power 5? Anybody? Look at A square. Look at the nature of A square. 0, 1, 1, 0 into 0, 1, 1, 0. First you need to write what is A square. What is the definition? Anybody? A into A. This is the definition. What is A? 0, 1, 1, 0. 0, 1, 1, 0. So what is this? 0 into 1, 0, 0 plus 1, 0, right? Next 0, 1 into 1, 1. So this is identity matrix. That means A square you are going to get identity matrix. Yes or no? So therefore you need to divide this 5 by this 2. What is the remainder? What is the remainder? 1. Therefore A power 5 by division algorithm, this can be written as 2 into 2 plus 1. That means A square A into 2 power A power 2 into 2 into A power 1. That means A square whole square into A power 1. That means A square is nothing but I square. A square A, what is A? A square I square into A. That means I square is nothing but I, and I into A is equals to A by identity property. So A power 5 is itself is A. Right? Suppose you're given a matrix 0 0 x 0 x 0 x 0 0. Suppose you're asked to find A power 100. Yeah, what is that? So what is the best technique? You need to do it. Compute A square. Look at the nature. Apply mathematical induction. You get the answer. So what is this? 0 0 x square 0 0 0 0 0 0 x 0 x square 0 0 0 x 0 x square x 0 0 0 0 0 0 x 0 plus 0 plus 0 next 0 x into x square plus 0 into 0 0 plus 0 into 0 0. So what you're going to get is x square like this. That means it can be rewritten as x square into I, where I is the 3 by 3 matrix. Right? A square is nothing but like this, but I require to find, see what I require actually, I require to find a power 100. So this can be rewritten as a square in whole power 50. But you know that a square is actually what? X square into I whole power 50. But this can be rewritten as x square whole power 50 into I power 50. Right? So that means x power 100 into I power 50 is I. Therefore, what is the answer? X power 100 into I. X power 100, not x power 100, because it is a matrix. Once you take you're asked to find a power 100, you're asked to find a power 100, that should be a matrix. If you remove I, the answer is not right. If you remove this I, the answer is not correct, because the number, it is a matrix. Can they be equal? No. So you need to write I. I power 100 is I. Right? Suppose you are given this a equals to x, suppose 0, 0, 1, 1, like this. You are asked to compute a plus a square plus a cube plus going on a power n. What is the answer? So what is the trick I am telling you? You need to compute a square and a cube. So a square is nothing but 0, 0, 1, 1, and 0, 0, 1, 1 is nothing but actually 0, 0, 0, next 0, 0, and 0, 0, 1, and 0, 1. That means what? It is exactly same as saying that a. Similarly, if you compute a cube, this is nothing but again you are going to get a, because a into a, again you are going to get a square. That is nothing but your a. So a power 4 also a. So by induction, a power n is a for every n. Right? So what you're asked to find? You're asked to find a plus a square plus going on a power n. Right? But this is exactly, precisely, a is nothing but a square also a cube also a, going on a power n also a. So how many s? N s. So what is our answer? Na. What is our answer? Na. Right? Suppose you're given like this. A is equals to 1, 2, 0, 1. You're asked to compute a power n, where n is a natural number. Your options are, suppose 1, n, 0, 1, b is equals to 2, n, 0, 1, c is equals to 1, n, 0, 2, d is equals to 1, 2, n, 0, 1. Yeah, what is right? What is right?
What option?
What is option? Yeah, anybody? What is option? What is option?
Fourth
D,
one,
sir. D, sir.
D, right? Good. Your option is D, because in order to compute all these things, see, there are two ticks actually. One thing is you need to compute a square. One thing is you can apply mathematical induction, because they are integral powers. So you take n equals to 1. That means a power 1. What is a power 1? A itself now. So when you plug n equals to 1, you're going to give actually 1, 1, 0, 1. This is not your a. So this is not your answer. See what your answer, if you plug n equals to 1, you're going to get actually a itself. A power 1 is equals to a itself. But the thing is that when you plug n equals to 1, you're not going to get a value by taking the option a. Right? If you take n equals to 1, so this is not same as saying your n, because here this is actually what? This is 2, this is what actually 1. So a power 1 should not be a. So this option is not right. Here when you plug a equals to n equals to 1, 1, 1, 0, 2. This is not a. Therefore, this is not in your option. Right? When you plug n equals to 1, 1, 2, 0, 1. This is your a. So this is your answer. Right? Whenever you are given integral multiples, so definitely one can solve the problem in two ways. One thing is applying mathematical induction. One thing is you need to compute a square, you need to compute a cube, then look at the nature, then applying mathematical induction. Right? Next is actually, I forgot to tell you one application. So one application is actually, this is very important application, you know, product of non-zero matrices may be zero. That means you take any, suppose you take any non-zero matrix, suppose you take in non-zero matrix, but the product could be a zero matrix, right? Suppose you can take 1 0 0 b equals to, you know, 0 0 1 0. What is your, you know, it is non-zero matrix. It is also non-zero matrix because at least one entry is non-zero. So therefore it is non-zero matrix. Therefore what is going to be, you know, 1 0 0 0 0 1 0 is nothing but what, 0 0 and 0 0 0 0 0 0. That means what, your, this is a matrix, it is a zero matrix. So that means product of non-zero matrix may be zero matrix. So using this operation, you know, this you know that actually this set of all matrices, you know, of course it is actually what is a abelian group with respect to addition. Okay, of course it is a ring actually, because actually you know that all properties are satisfied. It satisfies, you know, closure property, associative property, distributive properties you have seen, yes or no? So all the properties, closure property, associative property, distributive properties, all properties are satisfied. Of course it satisfies identity property also. It satisfies identity property also, provided they're conformable. So that means what, it, you know, it is a ring actually. The all matrices with respect to addition and scalar multiplication is a ring of matrices, right? It is a ring. Okay, it is a ring of matrices because all properties abelian group, and it satisfies, you know, closure property with respect to addition, and it satisfies matrix multiplication is associative, and matrix multiplication is distributive, and it satisfies identity property, right? So therefore it satisfies all properties, therefore it is a ring. Therefore it is a ring. Question is that is it an integral domain? Answer no, because it has a zero divisors, right? It has a zero divisors. No, because you know this is an example. Product of non-zero may be zero, so therefore it has a zero divisors. It has a zero divisors, so hence it is not integral domain. Hence it is not a field. Not integral domain. Right? Hence not a field. Right? It's a vector space. Okay, that is smooth. It is a ring. Okay, that is smooth, but it is not a field. It's not integral domain. Is it clear? Hello.
Yes, sir.
Next is sir Nagesh sir. Are you there? Hello sir.
Yeah, sir.
Yeah. Oh,
Sorry,
time
sir, are they?
7:16.
Ah.
Oh, sorry sir. I చూసుకోలేదు 7:16.
Oh, no problem. No problem. It's no problem. If you take within 2-3 minutes, you can close.
Yeah. అంటే నెక్స్ట్ వేరే కాన్సెప్ట్ ఉంది.
Then next close, gents. Next step.
So any doubts, sir? Any doubts?